The title of this section of the course is called the chain rule, and when you think about the name of it, it doesn't sound all that terribly important. I mean, so far we talked about derivatives and trigonometric derivatives and all these things. And then you get to this section called the chain rule, and then you move on into really other big topics like the integral and other things. Don't underestimate the importance of this section. The chain rule is the bread and butter of calculus. Specifically, it's really the bread and butter of taking derivatives. So far, I've shown you how to take some basic derivatives. I've given you a list of trig derivatives that are basically a list that's just given to you and say, hey, use these. And I've given you the tools to take derivative of polynomials like x squared, x to the third, and so on. And then I've given you some basic rules. You know, what if these things are added together? Functions of x, what do? Well, you take the derivative of the guys individually. What if they're multiplied? Well, then you've got a little bit more complicated thing to do. And what if they're divided? You know, some function of x divided by some function of x. Well, then you've got a little more hoops to jump through. But in the end, it's not that bad. The chain rule is going to tell you what do you do when you have functions of x kind of nested inside one of another. It's extremely powerful, and it's going to really open the door to let you take all kinds of derivatives of many types. You need to master the chain rule, and you need to understand it. So watch this section a few times if you're having problems. Well, I'm going to open with kind of an example, and I think I'll get your attention and kind of make you realize why it's important. What if I just told you, hey, take the derivative. What if you have the function sine of x squared? So it's not sine of x, it's sine of x squared. Okay? So if you were to plot this, you'd have to, for every value of x, you'd square it, and then you would take the sine. Okay? After you've squared the value, you take the sine. Well, at first glance, it says, well, this isn't so bad. I already know what the derivative of sine is. Okay? The derivative of sine, I've already told you this, is just equal to cosine. I've told you that. Okay? But this is not the same thing as this. You can't just sit here and say, this is the trap. You've got to make sure you don't fall into the trap. You can't look at this and say, well, since the derivative of sine is cosine, well, then the derivative of sine squared is just cosine x squared, like this. That's it. That's the derivative. No. Absolutely wrong. Okay? You cannot do that. The reason is, when I gave you those lists, that list there of derivatives, like the derivative of sine is cosine, that is true only for something that looks exactly like this. It has to be the sine of x, the cosine of x. It can't be the sine of the square root of x. It can't be the sine of 2x. It can't be the sine of x to the 10th. It has to be the sine of x, and then and only then, when you take the derivative, you get the cosine of x. You can't just generalize like what I just showed you, drew the big X through. But work with me here and this will be clear. You know this fact is true, and you also know that if you were to take the derivative of x squared by itself, just by itself, you would get 2x. I taught you both of those things individually. So, if you were to guess, this function has something to do with sine, so the derivative is going to have something to do with cosine, and it also has this function has something to do with x squared, so the derivative is going to have something to do with 2x. The question is, how are they related to one another? I'm going to tell you the answer, but I'm not going to tell you why, and I think it'll open the door. The derivative of this is the sine, whoops, started out wrong already. It's the cosine of x squared, okay, times 2x. You take these two results and you multiply them together. And another way to rewrite this is 2x times the cosine of x squared. Earlier, we were writing cosine squared x. That means cosine of x all squared. So you put an x in, take the cosine, then you square it. What I'm saying here is literally the cosine of x squared. So you put an x in, you square it, and then you take the cosine. These are different things here. Writing this and this, they're different things. Here I'm squaring the value before I take the cosine. Here I'm squaring the value after I take the cosine. But back to the main point, the derivative does involve the cosine of x. you got a cosine x squared here, and it does involve the derivative of the inside here, the unmodified part here on the inside, which was 2x. And what we did, we multiplied them together. That really is the chain rule. In essence, and I'm going to make it more formal in a minute, but in essence, what you're doing with the chain rule is, anytime you see something non-standard, in other words, something that you don't have a cookie-cutter formula for, but it kind of resembles something else, you take the derivative of the big picture, which is the sine of x squared, and you go ahead and apply it just like you would think common sense would tell you, and you would say, okay, well, derivative of sine is cosine, so cosine, but it was x squared, so it's got to be cosine x squared. But you can't stop there. You can't stop there. What you do is you keep multiplying by derivatives of the inside. The inside in this case is x squared. You take the derivative of that, you get 2x, you've got to multiply by that. So what you've done is, you take the derivative of the big picture, and then you keep going in and in and in and in and taking derivatives of the inside, in this case the inside's x squared, and keep multiplying the results together in one big string until you're down to basically nothing. So to formalize this, I'm going to put the formalization on the board only because it's going to be in your book, and you might look at it and roll your eyes and say, well, this isn't very useful. If you have a function of x, and another function of x. We're going to call them f and g. In this case, f is the sine of x, and in this case, g is x squared. And there's another function that I'm going to define big F that's related to these two by f of g of x. Now, these are not multiplied together. This means that in place of f of x, I stick the other function of x inside of it. I tuck it inside, which is what we did here. You have sine of x, but then you kind of tuck in x squared in place of the x, and so it's a function of x. The big picture is the sine of x, and you tucked in and you kind of snuck in the back door an x squared here in place of the x. So it's a function. The function of x is another function of x. It's called a nested function. Okay, so when you defined a function of a function like this, the derivative of that whole composite, it's really called a composite function, is just simply equal to the derivative of the big picture, which is exactly the derivative of f here I was telling you about, multiplied by the derivative of the inside, which is g of x. So it's exactly what I told you to do up above, okay? You've got the big picture, which is the function of f, and you take the derivative of that, leaving the inside kind of unchanged, so you carry your x squared down. You know the derivative of sine is cosine, you kind of leave your x squared alone because that's the big picture. But in order to complete it, you've got to take the derivative of the inside, which in this case is your g of x, and so you're multiplying by the derivative of g of x. In this case is simply 2x. That's why it's called a chain rule, because you've got to keep kind of going and going, and they're kind of linked to get together. Okay, you've got to link them together. So what are some other examples of functions that are nested like this, just to give you an idea of the kinds of things you're going to need to think about? Sine of 2x, that's a nested function because you're kind of tucking in a 2x here instead of a regular old sine x. Okay. What if you had, tangent of x to the fourth power, all inside of there? Well, that's kind of a nested function. Your big picture function is going to be the tangent of x, and then your function that you're kind of sneaking in, your g of x that goes kind of inside there, is x to the fourth. So anytime you see a function that looks familiar, but it's modified a little bit, then you're going to have to use the chain rule. And you can talk about this stuff all day long, but in the end, you really just need to work examples, and then you will get the hang of it. So let's do that. I like to teach by working examples because it makes things a whole lot more clear instead of just talking about stuff forever. What if you have g of x, and that's just simply equal to the square root of x squared minus 7x? Well, my advice right off the bat, anytime you see a square root, just go ahead and write it as an exponent. So x squared minus 7x 1/2 to the 1/2 power. Question is, take the derivative of that. I think you can convince yourself you can't simplify that anymore. You can't factor anything out. You can't actually take the square root of this. It's not a perfect square. You really can't do much else with it except stare at it and wonder what to do. And you might be tempted to say, geez, I have no idea how to take the derivative of that. Okay? But when you think about it, what's the big picture function here? The big picture, the f of x, the function that surrounds everything else. What is that? Well, that is x squared. Okay? I'm sorry, not x squared, x to the 1/2. That's the big picture function. What I'm doing is I've got some quantity here, and I'm taking the 1/2, raising it to the 1/2 power. Now inside here, it's a little more complicated than x. I've got x squared minus 7x, but the big picture, the f of x here, is equal to that. And then you got to say, well, what's the inside function? Well, that's just simply what's inside of here. So in the end, the way to take this derivative is, you take the derivative of the big picture function first. Now, how would you do that? If this were x to the 1/2, what would you do if you took the derivative? If you took the derivative of it, this is supposed to be a derivative mark, then what you would have is 1/2 comes out times x, and then you have 1/2 minus 1. So you have 1/2 times x to the negative 1/2 power. That's how you would take that derivative if it were simply this. Okay, but it's not. You've got something more complicated inside. So it's very simple. You put your 1/2 down just like you did before. And then you put exactly what's on the inside, x squared minus 7x. And in the exponent, you put negative 1/2. You do exactly what you would do if this were just simply x. Okay? 1/2 x, term here, to the minus 1/2. But because this is not x, you've got to multiply times the derivative of the inside. The derivative of the inside is simply 2x minus 7, right? Because derivative of x is 2x, derivative of minus 7x is 7, and we've already learned that before. So to kind of rewrite it, what you would have is 2x minus 7 on the top, and then you would have 2x squared minus 7x to the 1/2 on the bottom. All I did is I moved this negative 1/2 down to the bottom, made it a positive exponent. I left this in the numerator, and I have the 2 down with it. This is the answer. So when you look at this, the first thing you should look is the big picture. The big picture is I'm raising something to the 1/2 power. Boom, I know how to take derivatives of something raised to the power of 1/2. I've been doing that all day. I just write 1/2, then what's inside, and then to the negative 1/2. The same as I would if it looked just like this. But I'm not done because the inside is not so simple. So in order to fix that, I multiply by the derivative of the inside, which is just this, and then I get my answer. Get my answer. It is really not so hard, okay? It can just get tedious when your problems get hard. When the problems get, they can easily get out of control when you have a lot of nested things inside of each other. So let's go ahead and do another one. A fairly simple one to get our feet wet. What if you have tangent of 3x, like this? Well, you know what the tangent, I should ask you, what is the big picture function we're doing here? Well, we're taking the tangent of something. I know what the tangent of x is, okay, but that's not what I have here. So let's go ahead and go with that. Let's take the derivative of the big picture function first. Derivative of tangent, if you remember back from the previous section, is secant squared. Secant squared of what? Well, I leave everything completely unchanged at first. Secant squared of 3x. And you would think you could stop there, but you can't because you have to take the derivative of the inside. The derivative of the inside of this is just simply 3 because the derivative of 3x is 3. So to rewrite it, you have 3 times the secant squared of 3x. Okay? Now, before we go on, I want to open your eyes a little bit. Okay? You've been using this chain rule the entire time. I've been teaching you problems. It's just that I never told you it was a chain rule because it didn't matter until now. When you take this problem, what if the problem were simply tangent of x? And I'd say take the derivative. Well, you would immediately flip to your chart on the previous page and just immediately tell me, okay, it's a secant squared of x. And that's it. That is the answer. What you've been doing up until now is you've been applying the chain rule, because when you think about it, the big picture function is tangent of x. So I'd put that down and I say, okay, it's secant squared of x. But then I've got to, in the general sense, multiply by the derivative of the inside. The inside is simply x. The derivative of x is 1. So in the end, you have secant squared of x. So you see, you've been multiplying by the derivative of the inside the whole entire time. The same thing with, what if we have y is equal to x squared, and I say, take the derivative, and you say y prime, which is the derivative, is simply 2x, and you stop. And you say, that's the answer, Jason, because you told me. You put the exponent out, you put the x, and you have, subtract 1 out of the exponent, and boom, that's it. But no, reality says what you've had here is, you have x raised to the power of 2, like this, which is really the same thing as this. So the big picture function is something raised to the power of 2, okay? So I'll do 2 and then x and the 1 power. But again, I've multiplied by the derivative of the inside, which again is 1, okay? So all along, in all of these problems we've been doing, you've been applying the chain rule. It just so happens that the derivative of the inside has always been 1 up until now in all of these problems. Here, the derivative of the inside is not 1, so you've got to carry that along. And there's a lot of theory into why the chain rule works, and I could go and bore you with a bunch of stuff, but it's not going to change the fact that this is how you work the problems. What if you have y is equal to 1 plus cosine squared of x raised to the 6th power? Prior to now, you'd look at that and you'd say, I have no idea how to do that. But the big picture function is something raised to the 6th power. So you just say, okay, I'm going to treat it like that, and I'm going to say in the inside, I leave it unchanged. So the derivative is 6, and then you have the inside raised to the 5th power as if it were x to the 6th. That's exactly how I would have taken that derivative. But you can't stop there. You've got to multiply by the derivative of the inside. The derivative of 1 is simply 0. The derivative of cosine squared is another little trick, right? Because that's not exactly the same either. But the big picture function here is cosine squared, so I'm taking the square of something. So what I have here is 2 times the cosine of x. Okay, and again, I have to take the derivative of the inside here, which is derivative of cosine, which is negative sine of x. Now that was a lot of fast and furious stuff all at the same time. So I want to make sure that we're in sync before I move any farther. Put the 6 out, I wrote the inside down, put the 5 down, no problem. Now I've got to take the derivative of the inside. The derivative of this 1 is simply 0 because it's a constant. Okay? The derivative of cosine squared is really this. This is how you write cosine squared. So to take the derivative of this, I've got to do a chain rule again. Okay? The big picture function is squaring something, so I write 2 times the cosine of x, and then raised to the power of 1, because 2 minus 1 is 1, so I've got this. But I've got to take the derivative of the inside, and so the derivative of cosine, if you look back, is simply minus sine. So I've got another chain rule here just to take the derivative of this, and that's how I arrived at that. Okay, so you see how you can get to where you need to use the chain rule all the time. So to simplify this, you just simply have 6 times 1 plus cosine squared of x, the 5th power, times negative 2 cosine x sine of x, like this. Okay? Now you can take this 2 and multiply it by 6, and you'll get negative 12, and then you'll have this term here, and then you'll have what's left over from this term here. But basically, this is the answer. You just multiply 6 times negative 2, put it out here, and get a negative 12, and you've got the answer. So It looks complicated, but really you're doing the chain rule twice. You've got to do this first, and you get this term here, take the derivative of the inside, and you get this term here. But when you do that, you end up having to use the chain rule again, because this is not simply cosine of x, it's cosine squared of x. So you've got to use the chain rule. That's why I was telling you a minute ago that you really need to spend some time with this section, because you're going to find out that most of the functions that exist, they're all kind of nested like that. They're not so simple. So you have to use the chain rule and be comfortable with the chain rule in order to be able to get really many problems right at all. What if you had sine cubed of x plus cosine cubed of x? And in order to make this clear, I'm just going to write it like this, just so everyone's exactly clear what we're doing. This is exactly the same. I haven't done anything to it. I'm just writing it this way. Now to take the derivative, I think you'll agree with me that the big picture function is that we're cubing something, and the same here. So if I take the derivative of this guy, I'm going to have 3 times the sine of x to the second power, because I have the exponent minus 1, but then I'm going to multiply by the derivative of the inside. The derivative of sine is just simply cosine of x. Okay? Now I've got to deal with the second term, and it's going to be very similar. I'm going to have 3 times the cosine of x to the second power. Pull the 3 out, write the inside down, put a 2 up in the top. But then again, I've got to multiply by the derivative of the inside. And the derivative of a cosine is negative sine. Like this. Okay? So in order to simplify this, you're basically going to have 3 times sine squared of x cosine of x minus 3 cosine squared of x times sine of x. And really, all I've done there is pull that negative sign out and just kind of write everything over again, kind of like this. Now, this isn't too much of a simplification, but you can factor it a little bit further, and you can pull out of this what's common to both terms. Well, if 3 is common, okay, I've got 2 sine squared here, and I've got sine, so I can pull out 1 sine of x here. And I've got a cosine here and a cosine squared, so I can pull out another cosine of x here. And on the inside, what I'll have for this first term is just sine of x. Okay, and for what I'll have for the second term is just cosine of x. Just convince yourself that you're comfortable with that. If you take this and multiply it by this, you'll arrive at this, because sine times sine gives you sine squared, so you'll arrive back here. If you take this and multiply it by this, you'll get back this, because cosine times cosine gives you cosine squared. So that's the answer. You just got to look at the big picture function, figure out what you're doing. You take the derivative of each term separately and kind of add them up and go on. And you should work some problems on your own on these. I mean, I've picked a fairly good variety, I think, of good problems to show you the basic big picture here. But in order to really make really good progress, you need to move along and do some problems on your own, I think. What if you had a function that looks something like this? Tangent squared of x to the third. Well, the first thing I like to do is write it in a kind of a better way. So I'm going to write tangent of x to the third, and the entire thing is squared. So you've got tangent of x cubed, and you're squaring the entire thing. This is a really good example of the chain rule. What's the big picture? Well, you're squaring something. So let's do that first. Let's take the derivative. The 2 comes out of the exponent, and I leave the inside exactly alone. Tangent of x cubed. The exponent up here is going to be a 1, because 2 minus 1 is 1. Now, I've got to take the derivative of the inside. What's the big picture function here? It's tangent. What is the derivative of the tangent function? Secant squared. Again, I'm going to leave the inside here alone, because I'm taking the derivative of this. The big picture is tangent. Derivative of tangent, secant squared. Now, to move further, I've got to take the derivative of the inside again. Derivative of that is simply 3x squared. 3 comes out of the exponent, and then you have x squared. So here you did the chain rule kind of twice. You have 2 times, you kind of do the big one, so you have 2, and you have the inside raised to the first power, and then you're taking the tangent, which gives you secant squared. You leave the inside alone, and again, the derivative of the inside gives you that. So in the end, you're going to have 6x squared, this times this, times tangent of x to the third power times secant squared of x to the third power. And that's gonna get you there. Okay, so we'll do one final problem on the chain rule, just to kind of drive it home and work a problem of a little bit of a different type. What if you had f of x is equal to x minus 6 over x plus 7 cubed? Okay. Now, what's the big picture thing I'm doing? Well, first I'm cubing something. So, f prime of x, the derivative, is going to be equal to 3, and I'm going to leave the inside exactly alone. I'm not going to touch it. And then I'm going to raise it to the power of 2 because 3 minus 1 is 2. Now, I've got to take the derivative of the inside. This stuff, all of this stuff. Now, this is the division of two functions of x, so I've got to use that nasty formula that I used before to help me take derivatives of two functions of x divided by one another. How do I do that? It's the bottom, x plus 7, times the derivative of the top. Derivative of the top in this case is just 1, because the derivative of x is 1. The derivative of minus 6 is just 0, because that's a constant. So bottom times the derivative of the top minus the top, which is x minus 6, times the derivative of the bottom, again, that's just 1. Derivative of x is 1. Derivative of 7 is 0. All over bottom squared. X plus 7 squared. Okay. So, in order to simplify this more, let's just write it explicitly. X minus 6, x plus 7. I've done nothing here but rewrite it. And then over here, let's go ahead and expand all this stuff out. On the top, you'll have x plus 7 minus x plus 6 over x plus 7 squared. And I just kind of distributed this negative 1, and I got the negative x, I got the positive 6, like this. Now, what does that do? This x cancels with this negative x, right? Now, so in the end, what you're going to have is 3 times x minus 6, x plus 7. This quantity is squared, don't forget that. Over here, 7 plus 6 is 13. And on the bottom, you have x plus 7 again. This is squared. So really, in the end, what you're going to have is, you're going to have 3 times 13 is 39. You're going to have x minus 6 squared on the top. And on the bottom, you have an x plus 7. Remember, it's squared because you have this whole quantity squared, times an x plus 7 squared is going to give you x plus 7. You're going to have x plus 7 to the 4th power.